Trains on the moon. This is peak autism. Anthrofuturism. Rail can be up to 9 times more efficient than road because of 2 major advantages: aerodynamics and reduced rolling resistance friction. By chaining all the loads together into a big long line, trains experience less drag per ton, and steel wheels on steel rails have less rolling resistance. These are the 2 main benefits of rail, but a lesser benefit is the ability to steer a vehicle with flanged wheels. Despite this self-steering, trains still need a pilot for safety, but in mining applications, rails provide a sort of send and forget benefit that would go far on the moon. But rails are expensive to build, so you need to transport enough mass on them to justify the investment required to build them in the first place. This is the break-even point. In other words, you wouldn't build rails to only move a few tons on them. You only build rails if you are planning to move many, many tons. Tons of tons. But on the moon, we lack an atmosphere, so drag is not an additional benefit for trains. So to justify building a railway on the moon to reach that break-even point, the railway will need to move more mass than it otherwise would have to on Earth because rails have less of an advantage. Notice though that I said rails and not trains. We can get most of the benefits of scale using land trains. Today the term trains and rails are basically synonymous with each other, but that wasn't always the case, as modern trains on steel rails can trace their origins back to baggage trains on Roman roads. It wasn't until the mid-1550s that wooden rails, so-called pole roads, began to be used in coal mines and then wagonways in Central Europe. 200 years later, in the 1760s, as industrialization was underway, so much was being transported that the wooden rails of pole roads were being worn out fast enough that the Coalbrookdale Company began to fix plates of cast iron to the upper surface of their wooden rails to improve their life expectancy. 20 years after that, in the 1780s, Benjamin Outram went full metal and made the first plateway by using L-shaped plates instead of wooden poles with plate coverings. A decade later, in 1790, Outram and his new partner William Jessup tested a new idea on their wagonways: smooth-edged rails with flanged wheels, which eventually proved superior to plateways and became the standard for railways. Then the iron horse replaced the meat horse, and the rest is history. The interesting thing about this, though, is none of those technologies were particularly novel. It's not like wooden poles or metal plates were new ideas in the 16th century and had never occurred to anyone before. The Romans built aqueducts and roads and mass-produced metal for their armies. You don't think they could conceive of something as simple as a pole road? For all we know, they might have. We know they built grooved stone-tracked wagonways, so wooden poleways might have been used in isolated instances. But it definitely wasn't that common, or else we would know about it. What we do know is it didn't become widespread until the 1550s. Why? Well, wooden rails only made sense once the quantity of coal being transported was high enough that the investment made sense, and the quantity of coal being transported was dictated by the amount of coal being consumed by 16th century Central Europe, what you might call the overall economy. And that was dependent on the size of the population of 16th century Central Europe. And that population was reaching new heights in the 1550s because of the introduction of new staple crops introduced with the Columbian Exchange, combined with improvements in agricultural processes. So the Columbian Exchange led to more people, which created more consumption, which created more demand for transportation, which was the justification for investments into marginal improvements of transportation methods. So while the ability to do things is dependent on technology, when it makes sense to do them depends on the demands of the overall economy. So the question I want to figure out today is, at what point will a lunar economy be large enough to justify the creation of rails? But to answer that, we need to discuss what the alternative is. What would we be transporting mass on other than rails? The obvious answer is compact regolith roads. Simply compacting regolith using something like a road roller rover is the lowest form of terrain manipulation, and to build a railway, we will need to put rails on compact regolith. So really this would be the first step in building a railway. But at what point is it worth putting rails on that road? First, the build cost of the road. This discussion alone could be an entire video series. What vehicles are we using? How are they powered? What is their build cost and life expectancy? Where is our area of operations located? What is its topography? Any numbers we did come up with would be sort of sketchy or require very large error bars given all the context subject to change. So we cannot find an exact build cost. Fortunately, we don't have to because any rail system will be built on compact regolith, so it will cancel out. Therefore, we only care about the difference in build cost. What I mean by this is if a compact regolith road costs 1 megawatt hour a kilometer to build, then a rail will cost 1 megawatt hour a kilometer plus X. X being the extra cost to make the rails and ties, and X is the difference which determines the break-even point. We only need to find X. The build cost of the compact regolith road is not 0, but for us it is effectively 0. But to compare, we do need to find the amount of energy required to move 1 ton across 1 kilometer of compact regolith. When comparing each system, distance will be in the denominator in both cases, so it doesn't matter if it's 1 kilometer or 100. The cost scales either way, so we only need to look at tons per kilometer. This is a standard measurement, the ton kilometer or ton mile. Multiplying mass times gravity times the rolling resistance will give us the amount of newtons required. And since 1 joule is equal to 1 newton meter, if we add distance to our equation, we will get the energy cost in joules per kilometer. Since 1 watt hour is equal to 3,600 joules, we can then turn that number into watt hours per kilometer. We know our lunar gravity is 1.62 meters a second squared, and our distance is 1 kilometer or 1,000 meters. But what we don't know is what the rolling resistance is of compact lunar regolith, and without actual lab testing, we never will. So as usual, we have to use an imperfect Earth analog approximation. Simply searching around the internet for rolling resistance will lead you to various charts with everything from bike wheels on a wooden track to dirty tram rails. But most of the data in the charts, unsurprisingly, has to do with modern rubber car tires on various surfaces. As you can see, the material of the wheel has just as much of an impact on the rolling resistance as the surface it's rolling on. So we also need to quickly discuss what our wheels are going to be made of. Rubber will off-gas in a vacuum, and even if it doesn't, we don't really care about traction. We want low rolling resistance even on our land train. Even wagons on baggage trains used iron-plated wheels because metal wheels have high strength and low rolling resistance. So if a metal-wheeled vehicle on a compact regolith road sounds weird, just think about the freight carts and wagons of old. For our wheel material, our options are really just steel or a titanium metal alloy like tie metal. Maybe we can consider pure iron or an aluminum alloy, but that won't be nearly as strong, and even with 8 wheels per car, we'll still need way less material to make the wheels than the rails themselves, so this isn't an area where we should be cheap. Since titanium and its various alloys have a hardness equal to or greater than steel, and we have data for steel wheels, we'll use the steel wheel metric. But no, it can also be titanium, and if that's the case, the resistance might actually be even lower. So how do we get the rolling resistance of steel wheels on compact regolith? Unfortunately, we can't until someone does this in a lab using regolith Simulate or simulates it in a program. We actually do have rolling resistance data for wheels on lunar regolith, but all these studies have looked at rolling wheels on raw, uncompacted regolith, which has a much higher rolling resistance since the wheel is the thing compacting it. But I noticed that the Wikipedia page for rolling resistance has this strange entry about stagecoaches on earthen roads, and its reference says that it's from a book which lists a ton of rolling resistances for different animal-powered vehicles from 1914. I was curious about this and was able to track down a version of this book that was actually updated in 1919 and has tons of data as the Wikipedia note promised. But it doesn't list rolling resistance coefficients. Rather, it notes the traction power required in pounds per ton. But to calculate the rolling resistance coefficient, we simply use R equals F over W, with R being the rolling resistance coefficient, F being the force given, and W being the nominal load of the vehicle. Since this is in pounds per ton, we just divide the given number by 2,000 pounds. For example, this stagecoach on dirt road given in the Wikipedia corresponds to this entry in the table, earth road, very good. If we divide 77 pounds per ton by 2,000, we get 0.0385, which is exactly what the Wikipedia article lists. The really useful thing about this book is all the wheels are metal plated. The author calls them metal tires, which I believe refers to wooden wheels with metal plating, which is pretty common for wagons and carts, as mentioned earlier. This is useful because we intend to use metal wheels, but are going to have a really hard time finding modern data for metal wheels on different surfaces besides steel rails. But that's exactly what this is. Even if it's over a century old, the data is still there. So we have our wheels, but can any of these surfaces really be considered a close approximation of compact lunar regolith? Well, from those other studies, we know that the friction and texture of lunar regolith falls somewhere between dry sand and sandy loam, uncompacted, which makes sense. It is, after all, basically powdered basalt. And in another table, that old book lists the earth road surface as being either loam or clay. It doesn't say exactly which material is being counted in the other table, but I think it's obvious the good conditions entry corresponds to the hard, no dust, no ruts, nearly level loam road, which had the most number of trials. So the lunar regolith is like sandy loam, and here we have the rolling resistance for a compact loam road. There are so many issues with this, I know, but look, it's metal wheels on something approximating compact regolith. So I think we can at least say this is probably in the ballpark range, and hopefully soon someone can run experiments and get us actual data. But until then, I think this is the best I can do. For the wheel diameter, we know larger wheels move heavier loads easier, and we aren't worried about speed, so let's go with larger wheels. The largest wheels listed are those of the freight carts with a diameter of 80 inches, which is about 2 meters. Quite big, but not insane. And those 2-meter wheels have a 11.5 centimeter width. Wider wheels actually have lower rolling resistance because rolling resistance primarily arises from the deformation of the wheel and the surface it rolls on. A wider wheel spreads the load over a larger area, reducing the depth of deformation and thus the energy lost. But wide wheels on rails would require wide rails, which would mean more refined materials and thus an increased construction cost. Thinner wheels means thinner and therefore cheaper rails, but with higher rolling resistance. Since the compact regolith road isn't a rail, we can make our wheels as wide as we want. I mean, within reason. The wider the wheel, the heavier it is, so there's a trade-off and an optimal width. But we don't know what that would be. We only have data for 11.5 centimeter wide, 2 meter tall metal wheels on an earthen road, so we'll use this as our number. And know that we could maybe make the wheels a bit wider and have an even lower rolling resistance. And once we convert it from traction power to rolling resistance, we get a resistance of 0.022, which is about 2 times as much as tires on concrete and 10 times as much as steel train wheels on steel rails. Not great, but not terrible. Completing our equation, at this resistance, it would require about 35.6 joules to move 1 kilogram a kilometer, or 9.9 watt-hours per ton kilometer. This is really good, about 10 times as efficient as electric cars driving on paved concrete roads here on Earth, which consume about 200 watts a kilometer, or about 100 watts per ton kilometer, even though the compact regolith road has more rolling resistance than the tire on concrete. That 10x difference comes from 6 times the gravity and air resistance, which we don't have, so it's likely electric cars would have 10 times the range on a moon dirt road compared to a modern highway from these factors alone. Elon launched a Tesla to Mars. Which EV company wants to sponsor me to complete the first circumlunar navigation using their vehicle? It's only 7,000 miles, give or take, and with the extended range, that's like 2.5 charges. Tesla? Rivian? Ford? Vaz? I'll be waiting. So we don't need to know the build cost of the road, but we have the cost to transport a ton over a kilometer of it. So now we need to get the build cost of the steel railway and the cost to transport 1 ton over it. So to get the build cost of the railway, we need to figure out its dimensions, and that will tell us how much mass we need per kilometer. And then we can find out how much energy it will cost to refine that mass. Again, we are not counting terrain manipulation because that's going to basically be equal to the build cost of the compact regolith road, so it cancels out. To find the mass of the rail, we need to figure out the width and height of the rail. A standard rail car here on Earth has a gross weight between 130,000 and 140,000 kilograms. To keep it simple, let's just go with a nice round 100,000 kilogram weight, or 100 tons. Type 1080 steel has a tensile yield strength of 585 megapascals. If we add a safety factor of 1.25, our limit will be 468 megapascals. To support 100 tons and lunar gravity on 8 wheels, our rails will only need to be 2.16 millimeters wide. For reference, that's less than the width of a typical ice skating blade. And that's the problem with this approach. By just focusing on tensile yield strength, we are just measuring the downward force of a static load. This does give us some intuition into just how different lunar gravity is, but this is not a good method for estimating the mass of different rails because the rails are going to be subjected to lateral shearing forces, as well as compressive forces, as well as vibrations and thermal fluctuations. So really we need to take into account every force, fluctuation, and vibration, translate those to the best of our ability to fit the unique lunar environment, and then find the limits with a safety factor for each material. But since I'm not a masochist, let's just cheat. We can get a hint of how to cheat by thinking about why a 2mm rail is so absurd. It's too thin. It would snap. On the moon, we do have less gravity, but centrifugal forces are going to remain the same as on Earth or anywhere else. So this is actually our real failure point, meaning our rails will need to be designed to be thick enough to withstand these lateral forces. Since these forces are universal and we know Earth rails are already designed with these forces in mind, we can just use Earth rail widths, since this is the real failure point. But does that mean we won't get any savings from the lower lunar gravity? Well, we will from the amount of ties needed. The ties of a railway, not the steel rail itself, are the main load-bearing structures. And here we will save by needing less ties per kilometer for the same weight. But we'll have to come back to this, as we still need to find a rail size, and unfortunately there isn't just one single standard Earth rail size. There are lots of different sizes for different tracks in different regions and different time periods. But we aren't asking at what point does a modern heavy haul railway make sense over a regolith road. We're asking at what point does basically any rail system make sense. Our economy won't demand as much early on, and this corresponds with the historical evolution of rails here on Earth. Lighter, smaller rails were more common in the past, and the typical rail size slowly increased over the centuries as demand increased, a pattern which is likely to repeat on the moon. We do actually have historical data for smaller rails, and conveniently, rail sizes are already measured in mass per meter. So let's try to find the smallest rail with a modern design and use that. Wikipedia lists a bunch. Technically, the smallest rails are crane rails, but these serve a different purpose and aren't really designed for the centrifugal forces from turning, which is our universal failure point, the whole reason we are using an Earth rail design. So crane rails aren't a good measure for trains. The Wikipedia article notes that the American Society of Civil Engineers specified a bunch of rail profiles in 1893, so I checked this source to see if it gave good data for smaller rails, which it didn't. It just had a bunch of sketches of different rail sizes being used on the Pennsylvania Railway, and then a debate about rail head design. Interesting, but not particularly useful. But the article also talked about how rail standards were set over the course of a few years in the early 1900s by two other societies building off the ASCE's work, with the most recent being done by the American Railway Engineering Association, and the article referenced this book The Elements of Railroad Engineering, written in 1917. And oh man, this book is a goldmine. It talks about the manufacture of the rails, the chemical compositions and best practices for rolling them, gauging and thermal joint expansion, railhead design, and more. I can't express how much I love finding solutions to future problems in 100-year-old books, and this video has two. I rarely quote from sources, but this book gets right to the point, so I'm going to read it directly. The web, meaning the part of the rail between the head and the foot, need not be more than about a ½ inch thick, but the rail should be high to give stiffness. By stiffness is meant the reverse of flexibility, thus the deflection of a simple beam supported on points and loaded with a concentrated weight. A stiff track requires much less power to operate than a flexible track. Mr. Dudley's experiment showed from 75 to 100 horsepower per mile saved by an 80-pound rail as compared with a 65-pound rail. The stiffness of a rail varies with the cube of the height, but only proportionally with the width. Since the stiffer the track, the less the work of maintenance and the less the power necessary to haul trains, there is economy in heavy, high rails. So that's really interesting. There's actually a benefit to heavier rails derived from their stiffness. So heavier rails last longer and result in a higher transportation efficiency, but heavier rails means more mass, which is a higher upfront cost. So how do we choose the right size? Well, the book makes some recommendations based on industry experience. For light traffic, rails should be from 70 to 80 pounds. For heavy traffic lines, 90 to 100 pounds. While for lines or parts of lines having particularly heavy and frequent trains like in city terminals, 110-pound rails should be used. Instead of trying to model all the variables, energy saved per kilogram transported from rolling resistance and stiffness and rail life expectancy and construction costs derived from weight as the cube of height, and then amount of tons transported to break even with compact regolith, and then doing that for every single rail size to find the perfectly optimal one, and all this based on sketchy data and 100-year-old books, I think it's probably best if we just let 200 years of rail development function as a sort of natural genetic algorithm for us and go with the 70-pound rails, which is the minimum recommended for light rail traffic. 70 pounds per yard is 34.725 kilograms a meter. We know we need 2 rails, so we'll multiply that number by 2, and we need 1,000 meters per kilometer, so we need 69,450 kilograms of steel per kilometer of railway. Steel is mostly iron with a small percentage of carbon, silicon, and manganese. You will often see phosphorus and sulfur listed, but these are unwanted impurities which are hard to remove, so we won't count the energy cost to obtain them. Rather, we should count the energy cost to remove them, but we have much less phosphorus and sulfur on the moon, so they should be much less of an issue. I can't say there won't be any, but for all intents and purposes, we really just need to count iron, carbon, silicon, and manganese. For the fairest argument, we should use the cheapest form of iron gathering we know, which is going to be that cheap magnet beneficiation process from 1981, explained in depth in a previous video. Using this method, we can yield 184 kilograms of iron with trace amounts of nickel per hour at 76 kilowatts or 0.413 megawatt hours per ton. To melt this iron and do ladle metallurgy to make the steel, we don't have to use electricity. We can use a passive solar furnace using mirrors, whose production cost will be amortized across its entire lifespan, so its cost per ton should be negligible per kilometer of track. I should point out that nothing is free, but it should be a rounding error. Type 1080 steel has about 0.88% carbon, but more carbon makes the rails brittle, and best practices are about 0.5% carbon for 100-pound rails. On Earth, we have to remove carbon from steel, which is why cheaper steels have higher amounts of carbon. But on the moon, we have the opposite issue. We don't have enough carbon, so we have to add it to our melt. But a benefit of this is we can be very precise with exactly how much we add, so we can achieve any desired levels. So let's go with the recommended 0.5% carbon. So we have our steel formula: 99.3% iron, 0.5% carbon, 0.1% silicon, and 0.1% manganese. For 1 kilometer of rails, we'd need 68,964 kilograms of iron, 347 kilograms of carbon, and 69.5 kilograms of both silicon and manganese. We might be able to get carbon from lunar regolith by melting it and capturing the released CO2, but since lunar regolith only has about 0.0124% carbon, or just 200 grams per cubic meter, we'd need to melt 2,798,555 kilograms of regolith per kilometer of rel. It would be hard to capture the gases if we do this in a simple solar furnace, so really we're talking about pyrolysis, with the ability to separate out the CO2 via fractional distillation. We don't know how much it will cost to process regolith using pyrolysis, but we know that the Saturn V spent about 41.9 terajoules to deliver 43,000 kilograms to the moon's surface, or about 974.4 megajoules per kilogram, which would be about 0.27 megawatt hours per kilogram for the carbon. Raptor engines are about 25% more efficient than the F1, and we have the possibility of refueling on the moon, lowering it even more, but since no Starship has been to the moon, it's hard to know exactly what the cost will be in the future, so we'll go with this Saturn V number and just know it'll likely be lower in the future. So if we simply import our needed 347 kilograms of carbon per kilometer, then our carbon cost per kilometer will be 93.67 megawatt hours a kilometer. Since we need to process about 2.8 million kilograms of regolith with pyrolysis, to break even with imports, our pyrolysis method would need to be 8,060 times cheaper than imports, with a cost per kilogram of only 33.5 watts, about that of a light bulb. But this isn't really fair, because even if pyrolysis costs more in energy terms, the dollar costs will be lower. This is the issue with only using energy as our measure. Not all megawatts are made equal. It is definitely not fair to compare the megawatts required to move a kilogram from the Earth to the moon to the megawatts generated on the moon using a solar panel or something else. There is a giant gap between the value of these megawatts derived from what it took to generate them. Generating a megawatt using cheap solar panels is much cheaper in dollar terms than launching a kilogram to orbit using a rocket. But we don't have dollar data for either, so we are forced to use energy. And this is usually okay when we remain on the moon. But since it distills things down to their most basic physics, it causes some trickiness when we get into situations like this. We found the energy break-even point for pyrolysis versus imports, but if it costs 1,000 times less to generate a megawatt on the moon than to perform a megawatt of work using a rocket, we can essentially multiply our break-even cost by 1,000. So instead of 33.5 watts, it'd be 0.0335 megawatts. But that's the thing, we don't know if it's going to be 1,000 times cheaper to generate a megawatt on the moon versus a rocket's work, or 10,000, or 7,679. And that number will always be changing with new innovations. So until we have a market on the moon to dictate costs, we won't know at what point lunar-sourced carbon becomes cheaper than imported carbon from Earth, or even carbon imported from asteroids or elsewhere. We might get to this point if we can scale up our pyrolysis reactors and amortize their build cost across tens of thousands of tons of regolith, but that's just so many unknowns. So we are sort of forced to go with the Earth carbon import cost of 0.27 megawatt hours a kilogram, simply because we have the data for it. So that's carbon. What a mess. What about silicon and manganese? Well, lunar regolith is about 20% silicon and 0.2% manganese. For our steel, we need about 0.1% of each. Since refining enough manganese to achieve the required 0.1% would give us 100 times more silicon than needed, we only need to count the manganese cost. At 0.2% manganese per kilogram of regolith, to get 69.5 kilograms of manganese and a lot of silicon, we need to refine 500 kilograms to get both the silicon and manganese. Again, we don't know the pyrolysis cost, but a recent review of ISRU refining methods estimated molten regolith electrolysis to cost 0.42 megawatt hours a kilogram. Likely it will be higher, but using this number, we'd need 210 megawatt hours per kilometer for those elements. If instead we import the silicon and manganese, we'd need to import 139 kilograms total, 69.5 of each, which at the Saturn V cost of 0.27 megawatt hours a kilogram would be 37.53 megawatt hours a kilometer, 5 times less than using electrolysis. Again, these megawatts are not made equal, and it's likely the import megawatts will cost more than 5 times the cost of a lunar generated megawatt, but to keep everything fair and square, we'll go with the lower energy import cost since we are only counting energy because we know that this is the minimum energy required, even if it isn't representative of the actual financial cost. If that makes sense. I know, this is getting quite convoluted at this point. At the very least, this exercise has made me appreciate the power of decentralized price-setting markets more, as they generate all this value data in dollar terms organically through free agent auctions, which is sort of magical and makes everything way easier. Anyway, summing the corresponding energy costs, we get a rail cost of 159.7 megawatt hours per kilometer of rail. We're almost done, but the last thing we need to do is figure out the energy cost of making the ties. On Earth, we make these out of wood and more recently concrete and even plastic, but on the moon it makes sense to use sintered regolith. How big our ties are depends on how wide our rails are. The weight limit of train cars is determined by the axles, and shorter axles are stronger, which is why train cars are as wide as they are, about 1.5 meters wide. But on the moon, we have 1/6 the gravity, so for the same weight, we can either make our typical load-bearing axle wider, or we can make the car taller, or both. 6 times the standard gauge of 1.5 is 9 meters, but to be safe and account for going a bit taller, let's just go with 5 meters. So our ties will be 5 meters long and 0.2 meters wide and 0.2 meters thick. Sintered regolith has a density of 2 grams a cubic centimeter, so each tie will weigh 400 kilograms. The cross-tie spacing of mainline railroad concrete ties is approximately 60 centimeters. The compressive strength of concrete ties is about 60 to 80 megapascals. The compressive strength of sintered regolith is about 114 megapascals, 42.5% more than the strongest concrete ties, so we should be able to space them out about 42% more, meaning we need about 42% less ties per kilometer of track. This would be a spacing of 85.5 centimeters center to center, or 1,170 ties per kilometer. At 400 kilograms per tie, we'd need 468,000 kilograms of sintered regolith per kilometer. But we really didn't need to do any of that math because to create sintered regolith of this strength, all you have to do is melt it in a vacuum to 1050 degrees Celsius, which we can do in a solar furnace, same as we did for melting the iron to create steel. And since the solar furnace's production cost can be amortized across its entire lifespan, and we get the energy from the sun, its cost should be negligible per kilometer of track. We did this for the iron steel melting as well, so it is fair. Again, nothing is free, but it should be basically a rounding error. Also, the cost of transporting the ties and rails from production to construction, what we can call deployment, should be very small compared to the cost of producing the materials. Consider that the cost of transporting a kilogram on the compact regolith road is 9.9 watt hours per ton kilometer, and we need 468 tons of ties and rails per kilometer. This would be just 4.63 kilowatt hours per kilometer for deployment, or 0.463 megawatt hours per 100 kilometers transported. So not counting the cost to make the ties, our final cost for the railway is basically just that of creating the rails themselves, 159.7 megawatt hours per kilometer. Let's round that up to 160, which should be more than enough to cover the material transport cost, the production cost of the ties, and the cost of ladle metallurgy. Now, the last thing we need to do is figure out the energy cost to transport a kilogram on this steel rail, which is simple. The rolling resistance of steel wheels on a steel rail is about 0.002. So we get an energy cost of just 3.24 joules a kilogram a kilometer, or 0.9 watt hours per ton, about 91% more efficient than the compact regolith road. To break even with compact regolith ground transport, we would need to transport 17.8 million ton kilometers. That's the magic number. This sounds like a lot, But consider that 378 billion ton kilometers were transported by rail in just 2023 alone. In just the EU alone. In the US, it was 2.18 trillion ton kilometers in 2023 alone. It may not seem fair to compare the economy of the US and the EU to that of a fledgling lunar economy, but consider that the main point of industrializing the moon is to carve it up and use it as feedstock to build ships and stations. A single Stanford tourist station is about 10 million tons. An O'Neill cylinder is hundreds of billions of tons. So we do need to develop our lunar economy to EU levels in order to build O'Neill cylinders, and we know that development and railway infrastructure go hand in hand. But the ultimate determining question is whether or not this break-even point falls within the rail's life expectancy. And the answer is yes. The rail's life expectancy is 90.7 million tons. This number comes from our Holy Train book. When trying to find the life expectancy of modern rails, all I could find were estimates of time, 25 to 30 years or less, depending on traffic, which is really annoying because we need the amount of ton miles or ton kilometers. I think the reason they do this nowadays is because it's really impossible to tell exactly when a rail is going to wear out, so they do regular maintenance inspections, and then they just create time ranges for typical replacement schedules, which influences how frequently you inspect the rails. Fortunately though, our Holy Book delivers once again and lists the life expectancy of rails in tons. It also makes sense to use these numbers since we are using the same book's recommended rail design and steel composition, so everything is based on the same source. Taking the lower number of 100 million US tons gives us 90.7 million tons, but it could be even higher. So our 17.8 million ton break-even point falls well within the lower end estimated life expectancy of the rails. If we also counted the investment cost of setting up the systems required to manufacture the rails, the production lines and vehicles, then that investment is even better because it would pay off across not millions of tons, but rather multiple rail lifetimes, which is probably in the billions of tons. So we have just focused almost all of our effort on rails, but one of the biggest takeaways of this video that I want to draw your attention to is the fact that compact regolith roads are way better on the moon than even modern highways on Earth because there is less gravity and no atmospheric drag, so the advantage gap between rail and road is much smaller, with rails needing to transport a lot more before they are justified. But they are justified once you get to the point where you need to move millions of tons. How fast we get to that point, only time will tell, but I suspect it will happen quite quickly once lunar development begins in earnest. But why limit ourselves to just steel rails? What about pure iron or aluminum or titanium rails? Or even rails made from ceramic like sintered regolith?